So we'll start the second lecture of this week. So last Tuesday we covered elastic scattering and noted that the amplitude by this Q dot J and intensity is the square. Here I'm omitting this scattering amplitude and all that, right, to make it simple. And we saw how the periodicity of the system would change this intensity into a series of delta functions, Bragg peaks. Today, let's discuss something bigger than atom. For instance, colloid. What are colloid? Do you know what are colloids? What are the example of colloids? Typical example is milk. Okay, milk is a colloid. So what is milk made of? You know, comes out of cow. And, what is the largest ingredient of milk? Water. Water, right? It's mostly water. You're paying for water most of the time, but it's white, right? So it has. For instance, out of milk, what do you produce? For instance, if you take water out of milk, you get. Yeah, but what is the product? What's the first product out of the milk? In that dairy product? Butter, right, butter. Butter is what? Just a fat, okay? It has some protein in it, but fat, right? So milk is just water with fat, and the fat is oil. And so oil and water don't mix, right? So then, when baby try to drink milk, then you have to eat butter and then drink water. It doesn't work. So milk is made very nicely so that the fat is dispersed. Talking about this milk, okay? So milk is an oil or fat dispersed in water. So the way it is made is the fat is made into a very, very tiny particles, micron or so. And then they use protein as a surfactant because water and oil do not mix. First, the surfactant is kind of an organic molecule which brings water and oil together. One half of the surfactant is likes to be water, and the other one likes to be with oil. So they can mix these two. So essentially, that colloid is a dispersed particle of some kind of second object. It can be oil, it can be polymer, or it can be a hard particle. You can disperse silicate, for instance, in water if you use that correct surfactant. Anyway, the point is that this colloid is not an atomic object; it's a bigger object. Size, say, for instance, few thousand angstrom or so. So in order to study the size of this colloid, you don't have to worry about atomic level details. Right? So let's use, for instance, a wavelength, which is larger than atomic distances. Then you don't have to worry about atomic details. So instead of summation like that, we can use an approximation of density function. R over R that describes the atomic density, okay, where the density of atom at point R, and then E2 I2 of R, and instead of summation, you integrate over that. Okay? That the sort of continuum approximation instead of discrete approximation, discrete description of the atomic position. In the first equation, atoms are supposed to be a point, so at the point at Rj. Now in the second one, the atoms are so just like butter, it's spread in the space, okay, and we consider as a continuum object, okay. So rho of R tells you the atomic density at around at the position R, and here the resolution in real space is much larger, coarser than the atomic spacings, okay. So instead of each atom, you think about density of atom, okay. And again, length scale involved here is large, like 1,000 angstroms. So if R is large, that's 1,000, then relevant Q space would be small, yeah. Because Q times R is kind of order of 2 pi, right? So if R is large, then Q will be small. That means this scattering shows up at a small q. Small q means small sine theta, so it means small theta, right? That's why this is called small angle scattering. So in case of neutron scattering, it's called SANS, small angle neutron scattering. So in order to do the experiment, you have to make a very good collimated beam, an object, and measure this at a very, very small angle, okay? Very small angle. So quite often, the detector is very far away from the sample to catch a small angle. And of course, small, large is relative, okay? So we're talking about usually of the order of degree or less. Now, only problem is that you have to have a good collimated beam, otherwise a direct beam would burn your detector. Okay, so your beam has to be collimated, and then you have to have a nice beam stop. Okay, so you have to worry about the optics a little bit better than regular diffraction, but it's just a mechanics. And if you do that, you can measure this small angle scattering. So, how does this small angle scattering look like, and how do you interpret this? And that's the next step. So, to make things simpler, again, let's use one-dimensional approximation. Okay. So again, we are thinking about one-dimensional system called R, E2I, QR, DR, just one dimension, right? So let's start with a case where density in real space is like Gaussian. So this is rho bar. Okay, Gaussian kind of distribution. It's just an example. Okay, no real objects are really Gaussian, but if you have some kind of molecule, you can describe this density in terms of a Gaussian curve, right? There are more atoms at the center and less to the end. So the Gaussian curve is simply E2 minus R square over 2 sigma squared, where sigma is this much, right? When R is equal to sigma, the density is E2 1/2. E2 minus 1/2. Okay? So, the equation, this becomes integral of E2 IQ times E2 minus R squared over 2 sigma squared dr. Right? That's a funny integral, but you can rearrange it to so that you can integrate this out. So let's do it again, the same thing, but in a different way, so that it is exponential of how I take 2 sigma square out. Okay? Then you get R square minus 2I sigma square QR, right? And dr. Okay. So let's make this the smaller bracket into square. So this is equal to r minus I sigma square Q square. Not quite. This has a bit too much in it. So this plus sigma to the fourth Q squared, right? Now the whole thing is equal to exponential minus r minus I sigma square Q to square 2 sigma square dr, and then last term is outside this integration. So what you have is this and sigma square Q square over 2, right? Just rearrangement of terms. Then this integral is an integral from minus infinity to infinity, and this becomes a constant involving 2 pi and square root of 2 pi's. So that means this is a total thing is a constant times e to minus sigma square over 2 times Q square. Okay? And this is a Gaussian again. So Fourier transform of a Gaussian distribution is the Gaussian. That means okay, e2 minus sigma square over 2 times Q square. So that means e2 minus Q square over 2 Q sigma square, when Q sigma is equal to 1 over sigma. Right? So you start with the Gaussian with sigma, and then up with another Gaussian here is 1 over sigma. Right? So if a sigma is size, say 1,000 angstrom or so, then 1 over sigma is 1,000th of an angstrom, inverse angstrom. So 0.001 inverse angstrom. So atomic diffraction shows up at around 2 or 3 inverse angstroms. So this is way down in Q value. That means way down in sigma, very small angles. And that's what this is. And this is about phi. So intensity, which is square, becomes E2 minus sigma square Q square. Okay? So that means if you plot, oops, yeah. Okay, I'll get to the next page. So again, intensity is E2 minus sigma square Q square. Okay. So if you plot log of intensity against Q square, right? Against Q square, which is Q is proportional to sine theta, and theta is small, so Q is proportional to theta. So Q square is almost like theta square. Then you get the straight line. Okay, and from the slope you get this sigma square. The slope is supposed to be sigma square Q square. So this this happens all the time. If you do small angular scattering and plot log I against Q square, quite often you get linear line. So in this case, the subject is close to the Gaussian, at least approximately so. And then this sigma is called radius of gyration. In other case, so this is the quite often the case, but the object doesn't have to be Gaussian, right? Another extreme is that if the object or that the rho of R is well-defined function square, it's constant up to a certain sigma and then 0 beyond. Okay. You have a solid object like some tiny nano size metal. The density is constant inside, and beyond this radius, there's nothing. And this you can work out yourself also. Fourier transform or many terms. And if you do that, then you find that essentially the I becomes proportional to Q to the fourth. Because if you plot I to the Q to the fourth, then you get log of that, log of Q to the fourth. Log I versus log Q get minus a straight line. So usually you get this Q square law or Q fourth law. That's the easy case to understand. So again, Q square, if I is like a Q square, then it's a Gaussian case. And this case is called Guinier. Alex Guinier, who figured out first Guinier case. That's log of I is like minus Q square. And the other case is Porod for figure that out. In this case, I is like Q to 4. So again, if the object is kind of Gaussian, and so the perimeter or edge is not clear, if the edge is fuzzy, if the shape is fuzzy, it's not like a Gaussian, right? In this case, you get like linear law. But if interface is quite well defined, if it is like a solid object where that edge is clear, then you get Porod law. And yeah, in between you get this so-called fractal behavior. In other words, that if density follows some type of fractal behaviors, like density is R2 n rather than the R2 3, in this case, in a case of 3 dimensions. Right? Then you get fractional power law. In fact, one of the instructors that you hear later on, Professor Sari Seha, figured this out, and it's one of his important contribution that fractal small angular scattering can be defined this way. So small angle scattering gives you some idea about the size, okay, of the object, and also to some extent some shape. Not quite, right? Again, it's usually between q to the second and q to the fourth. So and many things are in between. So rarely you get really linear behavior or prolonged behavior, but sometimes you do. So you can have some idea about the shape of this object. So it is used quite often in the soft matter, or that when you study, macromolecular systems or polymers, some system with some kind of strong heterogeneity. If you have some precipitation or some distribution of second element. Now, so far we have been talking about just single colloid itself, which is fine if you have a low density. So here's an X-ray, and then here's a colloid, and then you get the small angle scattering. What happens if you have many colloids? Okay, high density. When the colloids are not completely uniformly distributed, but there are some kind of short range order. What do you think would happen? So in this case, instead of small angle scattering like that, this size reflects the size of each atom, right? Something like that. But then this distance between colloid, if this is random, you don't see anything, right? You simply see each colloid particle. But if they are higher in density, and this correlation becomes important, what do you think would happen? Right? So R becomes some kind of important length scale. That means inverse of that, 2 pi over R becomes important wavelength, right? So what happens is that instead of this, you get an intensity like that, sometimes like that. Some modulation of intensity. And the position of this peak relates to this distance R. We'll discuss it later when we discuss structure determination in next month. In this case, this is not exactly 2 pi over R. 2 pi is about 6.28, right? Now this shows up at around 7.8 or something instead of 2 pi. In fact, 2.5 times pi. And I explain you later on why that is the case. But anyway, the important point is not just this number. This number is detailed, not important. But the important thing is it's inversely related to R. So if the distance is large, then this the Q value is small. Okay, it's always the case. Q and R are inversely related. So some kind of short range order within the colloid would modulate this intensity, and some kind of peak would show up to tell you what kind of short range order you have. Right? So everything makes sense, right? And then this R is usually larger than 2 sigma. That means that this position is inside the 1 over sigma. Okay. So quite often that many research are done just to measure this small angle scattering and then radius of gyration. But that's the only first order business. And more people are now studying the interparticle correlations using this small angle scattering. And that's where the field is going. Okay, any question? In fact, any question from audience at other schools? Let me know if you have a question. Just type me, or you have a question? No? 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 Okay, let me change the subject and discuss so-called divide water factor. This is totally different subject. Now we go back to the crystal. Okay, we go back to the crystal, and so we're talking about crystals lined up like that. But in classical, physics, the atoms are not moving. But in quantum physics, atoms are never static, or that even in classical case, if you increase temperature, that the atom would vibrate. Right? So this effect produces many things, including inelastic scattering by phonon, because the lattice vibration is quantized as the phonon, and the divide factor. So later on in November, when I come back to this class again, I'll discuss the phonons, lattice vibrations. Right? What is the physics of lattice vibration, and how do you measure this lattice vibration by neutron inelastic scattering, and how to interpret the results of neutron inelastic scattering. Okay, so when I do that, I'll do this divide factor again, more sort of theoretical. But today, I'll give you sort of a more intuitive sort of way to understand this divide factor. Okay. So the intuitive way is to say that atoms are not, or atomic density is not like a delta function. It's not really, sitting at one place, but it's moving a little bit. At low temperature, because of a quantum fluctuation, atoms, by uncertainty principle, you cannot completely put atoms still. Okay. If what happens if you make the position of atom or electron infinitely small, then what's the origin of uncertainty principle? And why Einstein didn't like it? Einstein really didn't like that. He's one of the creators of quantum mechanics, but he didn't like the uncertainty principle. He said, maybe he said that God doesn't throw dice. So he thought there's something deeper behind. But anyway, it is a fact that in quantum mechanics, the position and momentum are related. Okay, so if you try to locate atom or electrons precisely, then momentum goes up. Okay, so the energy goes up. So for that reason, you just cannot, exactly locate the atom. So at low temperature, there's an uncertainty about the atomic position, and by an amplitude u, which is of the order of 0.1 angstrom at low temperature. And at high temperature, because of a thermal fluctuation, thermal agitation, that the atoms move more. So U amplitude increases. And at high temperature, U square is proportional to KT. Okay? So if you plot U square against T, then it goes like that. Okay? Linear at high temperature, and become constant at low temperature. Okay? We will do that later on when we discuss forms. So today, we just think that the atoms are distributed, like amplitude of 0.1 angstrom around the average position. So we can describe this in terms of density again. So instead of delta function, we use sigma of r. And the sigma of r actually is sum over sigma of sigma 0 of r minus this is j. Let's put j, rj. Around each point, rj, r1, r2, r3, etc. Around each position, which is an equilibrium or average position of the atom, you have some distribution. Okay. And let's use again at our rho of 0 Gaussian function. And I omit normalizer. R square minus 2u square. Okay? So you assume some kind of Gaussian distribution around this equilibrium position, and amplitude is u square. Okay? That means again the intensity, therefore, is sum over j over sigma 0 over r minus r j to e to iq r. Okay? Rj again is an equilibrium position. So we can switch the parameter so that this becomes equal to j sigma 0, and let's call this x, right? Then this becomes e2 minus well, here x is r minus rj. Okay, so rj is an r is x minus rj, x plus rj. So e to iq x plus rj. Then dx. Okay? So you can bring this rj in the front. So this becomes equal to j of e2 iq rj times sigma 0 x to way to iq x dx. Okay? So you get that. That becomes a regular delta function, right? So this is equal to delta of again q minus k, like we did last time, right? And then this integral is the one that we saw before, which is the integration of rho 0 x e to iqx dx, where rho 0 was e to minus x square minus 2 sigma square. Okay. So this becomes another Gaussian, right? Just like I did before. Again, I'm skipping the normalization constant. So this becomes e to minus q square sigma square over 2. Right? So that means intensity is square of that. So this becomes some of the, I'm sorry, not some. Some normalizer times, oops, delta of q minus k, the regular Bragg diffraction, times e2 minus, oh, I'm sorry, this is not sigma, it's a u. It's sigma is equal to u, so it becomes u. So it becomes u square, q square. Okay. So what happens is that the intensity is modulated by this factor, u square e2 minus u square times q square. Okay, here 2 is gone because this is phi, and then we square it, right? So 2 is gone. So the intensity series of diffraction is modulated by this factor. And u is small number, like 0.1 angstrom. Okay, so this is a very slowly varying function. This envelope e2 minus u square q square is a slowly varying envelope, and here is like 1 over u, and u is like 10th of angstrom, so it's like a 10 inverse angstrom. And diffraction peak appears before. So what happens is that they have lots of diffraction peaks, but intensity is modulated by this envelope, right? So if a position of the atom is static, you have a series of Bragg peaks, okay, forever. But intensity goes down if atom is not static, but moving a little bit. And that is the Debye-Waller factor. Debye-Waller factor. Debye-Waller factor. Quite often that people misunderstand this. For instance, people think that if scattering the atoms are static, you have this well-defined delta function, and if atoms are moving, then periodicity is lost. So this becomes like rodent, right? many people, even professionals, misunderstand that. This is not what happens. Okay, this is not what happens. The thermal fluctuation does not broaden diffraction peak. Right? It does not broaden diffraction peak. It simply reduces the amplitude of the diffraction peak. That's the Debye-Waller factor. Now, why that is the case? Why that is the case? Just physically, do you understand why instead this doesn't happen? Why the peak width like that? Peak widening of diffraction peak doesn't that happen? If you heat up a crystal, here's a crystal, you heat up a crystal, okay? In a sense that if you have a, extension of lattice, then the correlation here and correlations here are not correlated, right? So that you may say the correlation length becomes shorter. That means it should, produce a broader peak, right? See what I mean? That it's like a breaking up crystal into small regions, right? Therefore, it's crystal becoming big crystal becoming nano crystal. If that is the case, you should see a broad peak. But that is not the case, and you simply see the reduction in intensity. What? Why? That's a very intelligent answer. One of our students here answered. The reason is that the phonon does not produce any extra periodicity. Phonon has many periodicities, of course. So you are introducing periodicity, but you are introducing many periodicities in a sort of random fashion. So no one is accentuated. That's a good answer. Anything else? Anything else? This actually is a pretty deep concept and relates to the concept of long-range order. Long-range order. And that means that atoms are here, and each atom is vibrating, but average position R1 and Rj is not changing. Right? Okay, so there's some blurriness, but in terms of predicting the average position, time average position, there is a long range order. That means, as long as it is a crystal, you can predict miles away where the atom should be. Okay, here long means really long, macroscopic length. Because if you have a crystal here and you heat it up, atoms are vibrating, but the sample itself is not vibrating like that, right? sample length is not changing. Okay, so atomistic vibration is happening, but there's no macroscopic vibration. That means, you can predict where atoms are in average for long distance. So coherence length of this average position is infinite, or sample size, okay? So actual atomic motion becomes incoherent, okay? Because this atom may be here, this atom may be there, right? This kind of dynamic correlation is lost. But in time average, the coherence length is infinite. So if you do a measurement which corresponds to a long time average, that is that static diffraction, omega equals 0, and that elastic measurement does not exchange momentum with each atom. Elastic measurement exchanges momentum with the whole sample. Okay, so in this case, the order or atomic position of time averaged whole sample remains the same. Delta omega 0 means T is infinite, right? Omega and T are reciprocally connected. So omega 0 means the inverse of that tau relaxation time is infinite. That means you are time averaging the structure. So if you do elastic measurement gives you time average structure. So if you time average, then this kind of a small atomic vibration is gone. Right? You only see the individual atomic position. That's why you have infinite radiation length, and the Bragg diffraction peak is very, very sharp. Okay, that's the reason. If, however, if you do a different kind of measurement, in which omega is not 0, yeah? If you don't do the elastic measurement, but if you do inelastic measurement, then we are really measuring photons. So in this case, you don't get, the delta function-like response. You measure the energy and lifetime of each photon, and lifetime of each photon is not that long, so a nanosecond or so. So you get the finite width of this scattering. Okay. So again, elastic interaction, elastic scattering does not see each photon, but simply see the average, time averaged atomic positions. So you do not reduce the long range order, simply the intensity becomes reduced, because if a wavelength is large, that means Q, inverse of Q becomes small. So at a small Q, one over Q corresponds to real space length scale. Yeah, at a small length scale, if the atom is not static, then you don't know where it is. Right? If our atomic position is delta function-like, then no matter how big the Q is, you can always tell where the atom is. But if a Q is so large that Q is larger than, say, 1 over U, okay? Then the phase changes a lot within the atomic position. So you don't know where the atom is. So you don't see where the atom is. That's why the intensity goes down at high Q. Okay? So that is the bipolar factor. Again, it does not change the diffraction peak position, but it changes intensity. Now, I discussed the case of the bipolar factor due to this 0-point fluctuation and also phonon excitation. So this the bipolar factor increases or become more quickly decreasing at higher temperature. But frequently you see other sources of so-called bipolar factor. If you determine the bipolar factor from U, ideally, as I said, ideally temperature and U square. Ideally, you should do behavior like that. Quite often, you see behavior like that, or maybe it's not like that. Quite often, you see U value much bigger than 0.1. Photon, you can calculate the amplitude of photon at low temperature. I just said 0.1, but it depends on materials. Okay, usually of that order, but it's not the same from one to the other. But you can calculate that, and I'll do that when we discuss photon. Yeah, how to calculate this amplitude. So compared to that, the measured U can be larger. We run into this all the time. So what happens when you get U larger than expected? That means the measurement, if you measure intensity as a function of Q, you expect this kind of decrease in intensity. But if you do real measurement, it decreases much more quickly, right? So in this case, apparent U is large. Even at low temperature, you have large value of U. This happens if a system is not perfectly periodic. Okay? If you're looking at silicon or diamond, then you never see that. But in real materials, you are quite often looking at some kind of mixed compound, right? high temperature superconductor are very, very complex. All these interesting materials are complex. You're often mixing two kinds of different elements. And also that the lattice is not perfect. You have lattice imperfection. Sometimes you have some, crystals make mistakes, okay? And you have defects. So all these defects and this local mixing and this kind of disorder, randomness, produces apparent U, which is not due to phonon. Right? So there are two kinds of this Debye factor U. One is phonon, which you can calculate. The other one depends on the sample imperfection, disorder in the system. If you mix two elements, you're bound to have displacement. For instance, if you have big and small atoms, okay, then average position is not going to be totally periodic, right? It's deviated from total periodicity in global way. Yeah? This one is a little bit to the right, and etc. Right? So this kind of size differences produces apparent displacement. Okay, because this one compared to the average is moved a little bit, and this one also moved a little bit, and this one is moved a little bit to the left, etc. Right? So this kind of randomness produces apparent phonon. This is not a phonon. It's an atomic displacement due to this randomness. And this happens all the time in the sample. So when you measure the Debye factor, quite often you measure this type of displacement. So you have to be able to tell difference between the real Debye factor and extrinsic Debye factor, such as these. And later on, I'll discuss the method of paired density function PDF approach, in which we can see this type of disorder more directly, okay, much more clearly. But when you see large Debye factor, it's already clear indication that system is not perfect, but it has some local disorder in this. Okay, so that is about disorder and Debye factor. And at the end, I'd like to end this class of elastic scattering about the initial point that we discussed. Okay, in the beginning, I said, by definition, all scattering is inelastic, right? Because you have to conserve momentum and energy. So inherently, all scattering is inelastic. But in case of elastic scattering, you are transferring momentum to the whole sample. Therefore, the mass of the system is quite large. Therefore, transferred energy is negligibly small. So in this case, we can consider this as an elastic scattering. Now, this is fine. Again, we are looking at big diamond or silicon, some big crystal. But in real crystals are not like that. The real systems are not necessarily like that. And often, more and more often that you guys are studying more complex materials like nanomaterials or much more complex, heterogeneous materials. For instance, something is confined in the nanoscale, right? And these kind of complexities. So what happens if you do that? So in a nutshell, what happens is the quasi-elastic scattering. Something in between elastic scattering and inelastic scattering. Okay, whenever you see something like quasi, or you have to be careful. You have to exactly know what you're talking about. Otherwise, you're fooling yourself. Now, quasi-elastic scattering is that scattering which is almost elastic. So this is a elastic scattering, right? And the width delta E is determined by machine, by the resolution of the machine. It depends on what kind of monochondria you have, or chopper if you are dealing with the pulse source. And if you have a high enough resolution, what you see is intensity like that. Okay, so average transfer of energy is 0. Average is 0. But you do have some width wider than elastic. Okay, so that is called quasi-elastic scattering. And it happens all the time in small-scale systems, or some kind of gels or liquid, something which is not quite a solid. Okay. For instance, liquid has no elastic scattering. Everything is quasi-elastic, because in case of liquid, you just cannot, you cannot take the whole liquid out, right? Same way that neutron cannot transfer the momentum to the whole body of liquid because they are not connected. Okay? So what happens is that they partially transfer momentum, and you get quasi-elastic scattering. And the same way that you have this from this, for instance, surface water, or that the subsystem is trapped in nano cage, or that the small molecules. Okay, if a molecule is kind of stuck on the surface, then you get a quasi-elastic response. So you hear later on not only inelastic scattering, but the quasi-elastic scattering. This also happens near the phase transition. When the second order phase transition, the fluctuation becomes slower and slower. Right? As you go close to the critical point, then what happens is a so-called critical slowing down. Happens, excitation becomes slower and slower, and you start to see this quasi-elastic scattering. So I just wanted to say that elastic scattering looks simple, okay, but actually it happens only for good crystalline systems. If we have a big crystalline body, then you have energy transfer like 10⁻20, delta E over E of 10⁻20. In this case, it's totally, in all practice, it's elastic. But that happens only when you have a big crystal. If you have a tiny body, or gels, liquid, then you're not going to have that. You have something in between inelastic and elastic. So quasi-elastic is, of course, inelastic, strictly speaking, right? But inelastic scattering from a sort of a slow, low-frequency, diffuse mode. Instead of well-defined mode like photons, there are some local diffuse mode, and these create is a quasi-elastic scattering. So when you say elastic scattering, a simple case of the black peak, that's easy. But if you have more complex systems, disordered systems, then you make a kind of transition from simple elastic scattering to quasi-elastic to inelastic. So the case of liquid, indeed, is again, as I said, case in point, it's all inelastic. Okay? And then depending on the temperature of liquid, if you use so-called supercooled liquid, that is not high temperature liquid, but in between regular liquid and glass. Okay? If you cool liquid, the liquid viscosity starts to go up and become higher and higher. Dynamics become slower and slower, and finally it becomes a glass. And in this process, viscosity changes like 15 orders of magnitude, huge amount, okay? Huge amount of change. And then in the process, this scattering process changes from inelastic to quasi-elastic to apparently elastic. Because 15 orders of magnitude cannot cover this our resolution, okay? So in our measurement, usually, delta E over E is like 1% or 10th of a percent. In this case, quasi-elastic becomes elastic. But there are new techniques which you can measure this energy with much higher resolution. For instance, backscattering spectrometer has a much higher resolution. Spin echo provides you the resolution of a microvolt or even better. Usually we're talking about millivolt, right? Milli electron volt. But new techniques give you the resolution of microvolt and getting better. So that time scale is already not far away from the time scale of nuclear magnetic resonance, NMR. So NMR is used in studying a complex structure, complex dynamics of complex systems. But neutron is now accessing the time scale, which traditionally has been studied by NMR. But the difference between neutron and NMR is question was NMR is a local probe. Well, yes and no. I mean, yes, it's a local probe in a certain sense that you use nuclear spin, right? And then coherence is not there, right? That is correct. But at the same time, what is the momentum or Q of NMR? NMR is just electromagnetic wave, right? Well, it's everything, right? If you for static NMR, the Q equals 0, and for dynamic NMR, for instance, if you measure T1, everything contributes. So it is integrated over Q. Yeah, the local probe in a sense. You integrate all Q, therefore it becomes local. Right? Now, neutron is Q dependent, so you can resolve the momentum dependence. So you can study the phenomena at the level of microvolt and still resolve with the momentum. So that is important. So in many cases of complex interactions that in soft matter, it is a key. And this is only beginning. So soft matter has been studied so far by mainly using NMR. But now using these techniques, we are beginning to understand this very complex interaction in soft matter by resolving Q space. So yes, we can go beyond the local probe by using neutron scattering and start to understand the collective behavior. So I try to bridge the gap between inelastic and elastic. It's all connected. It's just a question of the time scale. And the real materials quite often show something in between, which is quasi-elastic scattering. And again, to summarize, coming back to elastic scattering, it's easy. Just E2 I Q R J, and I is does everything. So it's just a Fourier transform, right? Fourier transform of atomic position gives you phi, and the square of that gives you intensity. And just one more word. If that is the case, then it's just a Fourier transform. So you should be able to get know the atomic position right away from this diffraction measurement. It's just Fourier transforms. You should get the RJ right away. Why not? Why not? This is like a quantum mechanics. In quantum mechanics, you can never measure wave function, right? You can only measure probability, which is a square. The same here. That's a wave function. And you cannot measure that. You only measure intensity, which is square of this amplitude. Therefore, by squaring, what do you lose? Phase information. Phase information. Okay? So if you know the phase of a wave function, then you know atomic position. But you only know the square of the wave function, amplitude. Therefore, you don't have phase information. So all this diffraction experiment simply loses this phase information. So there have been a lot of effort to recover this phase information, and lots of research done in X-rays and neutron too. But basically, you lose it, right? So we try to regain this by kind of a trick, and no tricks works perfectly. So the short answer is that you don't get it. Okay, you never get it right. So we have to be humble. Actually, this is fine. If it is so easy, and if you Fourier transform gets you atomic position, you don't need PhD. you don't need PhD scientists. Elementary school student can do that. Okay. So elastic scattering becomes trivial if you have an access to the wave function. But we don't. So we have to think, and we have to be clever, and then get to the answer by various means. So that's all we need to know about elastic scattering. Thank you.